this architecture, two-dimensional array of RAM cells, this appears to be okay logically, but practically there is some implementation problem. The problem is like this: if we have only one decoder like this, which selects one of the rows, all the cells in a particular row, then you consider a situation. So suppose I want to have a memory which will have, say, 1 mega locations. So 1 mega locations means I have to have 20 address lines. Now every location may consist of, say, 1 memory cell, it may consist of 2 memory cells, 3 memory cells, and so on. But what I need is I have to have 20 address lines to address different locations or different rows in the cell array. Okay. So if I have these 20 address lines, then you consider what is the decoder complexity. In the decoder, I need 2 to the power 20 number of gates, AND gates, because the decoder logic is simply like something like this. It is nothing but an array of AND gates. Okay. So if I want to have simply a 2 to 4 decoder, which will have 2 lines, say A0 and A1. Okay. The connection will be something like this. So when both A0 and A1, they are 0, 0, in that case this output will be high. For 0, 1, this output will be high. For 1, 0, this output will be high. For 1, 1, this output will be high. Okay. So for a 20 input decoder, I have to add 2 to the power 20 number of AND gates. Okay. Every AND gate has to have a fan in of 20. Isn't it? 20. So just like this, in this case, every AND gate has 2 input lines. For a 2 to the power 20 to 2 to the power 20 decoder, I have to have 2 to the power 20 number of AND gates. Every AND gate will have to have 20 input lines. Okay, that is quite difficult. So instead of doing this, if we break the address into 2 components, okay. So these 20 address lines I break into 2 groups, 10, 10 each. And I say that out of these 20 address lines I will consider as row address, and these 10 address lines I will call as column address. Okay. And accordingly, I will have 2 decoders. One of them will be called as row address decoder, other one will be called as column address decoder. So the decoder complexity will come down drastically. For row address decoder, I need 2 to the power 10 number of AND gates. Each AND gate will have 10 input lines. For this, I need again 2 to the power 10 number of AND gates, which will again need AND gates of 10 inputs each. So the number of AND gates that you need is 2 to the power 10 plus 2 to the power 10, that is 2 to the power 12, 2 to the power 11. Whereas in the original configuration, the number of AND gates was 2 to the power 20. Okay. So number of AND gates has been reduced to a great extent. Not only that, the fan-in of every AND gate has also been halved. So instead of directly trying for only one decoder for decoding all the address lines, you break the address lines into 2 components. One of them you call as row address, and the other set you call as column address. Accordingly, you have 2 decoders. One is the row address decoder, other one is the column address decoder. And by making use of these 2 decoders, I can select different cells in the 2-dimensional cell array. Okay. So using this, if I want to implement a memory, let us take a memory of say 64K, where every location will contain just 1 bit. So I want to have a 64K by 1 memory organization. Following this architecture, it is 64K means I have to have 16 address lines. Okay. So if I follow this architecture, I need a decoder which will decode 16 to 2 to the power 16 outputs. For 16 inputs, it will give me 2 to the power 16 outputs. That means I need 2 to the power 16 number of AND gates. Every AND gate will have a fan-in of 16. Okay. Instead of doing this, I will break this 16 address lines into 2 groups, each of 8 bits. So I will break it into 8 plus 8 address lines. Okay. One group of 8 address lines I will call as row address, and the other group of 8 address lines I will call as column address. The cell, memory cells, will again be arranged in the form of a 2-dimensional array. Okay. And it will be 2 to the power 8 by 2 to the power 8. That means 256 by 256 cell array. Okay. That means every row will have 256 cells, and I will have 256 number of such cells. Okay. The 8 address lines, which I call as row address, that is fed to a 8 to 2 to the power 8 decoder. So 8 to 256 decoder. It will have 8 address lines as input. Okay. So let me mark them as address lines A0 to A7. The decoder have 256 output lines. Depending upon the bit combination on these 8 inputs, one of these 256 output lines will be active, right? And the corresponding row in this 2-dimensional cell array will be selected, right? So when a row is selected, that means all the cells in that particular row will be available either for reading operation or for writing operation. Now, out of these 256 cells belonging to a particular row, I have to select one particular cell, because my organization is 256K by 1 memory organization. So when I am selecting a particular row either for reading operation or for writing operation, I am selecting all the 256 cells belonging to a particular row with the help of this row address decoder. Okay. Next, what I have to do is, out of those 256 cells, I have to select a particular cell for reading or writing operation, and which cell I have to select, that will be dictated by the cell by the column address. That is again another 8 bits. Okay. So the arrangement in this case that can be made is, instead of simply a decoder, I can have a multiplexer demultiplexer combination. Okay. So if I want to perform a read operation of a particular bit, I pass all these 256 cell outputs through a 256 to 1 multiplexer, right? If I want to select a particular cell for write operation, at the output of this I have a single data line. So this is line D, both for reading operation and writing operation, assuming that external data bus that we have is a bidirectional data bus. So for reading operation, out of these 256 cells, output of one of them will be available on the output data bus. For writing operation, the data which is fed to this data line has to reach one out of these 256 cells. Okay. So, for reading operation, I need a 256 to 1 multiplexer. Okay. For writing operation, I need just the reverse 1 to 256 demultiplexer. Okay. And these demultiplexer select lines actually come from the column address. Okay. So, here I will have 8 lines, 8 address lines named say A8 to A15. Okay. Between the cell array and this multiplexer demultiplexer pair, I have 256 lines. Right. Now, in addition to these address lines, I also have to have the control signals like read write bar. Okay. I also have to have another control signal which we will call as chip select. Okay. So, here what we are doing is using this row address which is 8 bits, I am selecting one of the rows in this 2-dimensional cell array. Right? A row means 256 number of cells. When I want to read a particular location, that means I have to read a particular bit, a particular cell in that 256 cells. So, which cell I want to read, that depends upon what address is being fed to A8 to A15 lines. Depending upon that, one of these 256 will be selected and will be available at the output of the multiplexer. Similarly, for writing operation, I am selecting an entire row, but the data will reach only that particular cell which is fed by this 1 to 256 demultiplexer. Again, the selection of a particular cell through this demultiplexer will be done by this column address lines. Okay. So, you find that I gain tremendously if I break all the address lines into 2 components, row address and the column address. So, this is the organization of SS64K by 1 memory chip. The same cell array can also be thought of like this. I can, with slight modification, I can make it SS16K by 4 memory organization. You find that the number of cells are same. In this case also I have 64K cells. In the earlier case also we had 64 cells, 64K cells. But the cell organization in this case will be slightly different. Here, all these 64K cells we can put into 4 different arrays. So, I will have 4 256 by 64 cell array. Okay. So, instead of a single cell array, now we use 4 2-dimensional cell arrays. Every cell array will have 256 rows. Every row will consist of 64 cells. Right? Now, because I have 16K locations, that means number of bits needed to address these 16K locations is 14. Because 2 to the power 14 is 16K. These 14 lines I break again in the form of row address and column address. I will assume that 8 of these address lines A0 to A7 will be the row address. Okay. And the remaining 6 address lines A8 to A13 will be the column address. So, as before, because I have 8 address lines identified as row address, so I have to have a decoder that is 8 to 256 decoder. Okay. These decoders will have 8 address line inputs, A0 to A8. It will give 256 output lines. One of them will be active at a time depending upon this bit combination on the input side. So, whichever output line is active, the corresponding rows, because now I have 4 such cell arrays, so it will select 4 rows, one from each of the array, right. Here, in the earlier case, we had only one multiplexer and demultiplexer. But now, because we have 4 such arrays, so I need 4 64 to 1 multiplexer, one multiplexer for each of the cell array. Okay. I also need 4 1 to 64 demultiplexer. I will have 4 input output lines, one from each of the cell array. Let me mark them as D0, D1, D2 and D3. This input, this unit, the multiplexer demultiplexer unit, will get the column address, which consists of 6 lines, and the addresses from A8 to A13. Okay. It will have control inputs, read, write bar. It will also have control inputs, a chip select. Okay. And now, here I need 4 such connections, each of width 64. Okay. So, you find that by making use of various organizations, various kinds of chip arrays, I can go for different kinds of memory organization. But the basic structure will be like this. I have to have a row decoder, I have to have a column decoder. That row decoder will select an entire row consisting of a number of memory cells, and the column decoder will select one or more cells depending upon what is the memory organization from the cells coming from a particular row. Is it okay? Now, let us see practically how these cells are implemented. You find that as we have said in the cell architecture, the basic storage element is only this, which stores the bit either 0 or 1. But I have a number of additional gates for every cell, and the number of gates which are used to control this cell is much more than the number of gates which are actually used to store the value. That means the control overhead is much more than the storage overhead. Naturally, this is not an architecture which is desirable. Okay. So, for implementation, and particularly many of you have become expert in VLSI by this time. So, particularly for VLSI implementation, we have to keep in mind that the number of components should be reduced as much as possible. So, for practical implementation, each of these cells is implemented by using a model which is called a 6 transistor model. And it is very simple. Every cell will be something like this. So it is something like this. This is a particular cell. Okay. Now find that this cell consists of 6 transistors, because each of these inverters can be implemented using a single transistor. Okay. Now the cell is, all the cells belonging to a particular row is selected by this word line Wj, which actually comes from the row address decoder. Okay. And using the column select from the column address decoder, actually there are a number of columns like this. If I repeat this same architecture one after another, this becomes a number of columns. Okay. And the rows will consist of these cells arranged one over the other. Okay. Now see that how do you write the data into this cell, or how do you read the data from this cell? Whenever we want to write a data, say data 1 in this cell, what we have to do is we have to drive this BI line. This is called a dual rel. Okay. I have to drive BI line to high and BI complement line to low. So with BI line to high and BI complement line to low, if you select this particular word line, in that case, 1 will be written in this latch. You find that this is nothing but a latch. So what is the difference? The difference is the NOR gate has been replaced by an inverter. Okay. So if I set this line to high and this line to low, and select this particular cell by through this word line Wj, in that case 1 will be written in this cell. Similarly, if we want to write a 0, I have to drive BI line to 0, BI complement line to high or 1, and select this cell through this word line Wj. Okay. In that case 0 will be written in this cell. At the input, you are giving only a single bit, either 0 or 1. So that bit has to be converted to a complement pair. If I give an input 1, that has to be converted to 1 and 0. BI line has to be 1 and BI complement line has to be 0. So which is to be done by this unit? This is actually sense right amplifier. Along with that, this line also performs the additional task of driving lines BI and BI complement, both for reading purpose and writing purpose. Okay. So I can put it, it is sense right amplifier cum driver. Okay. Similarly, if I want to read this particular memory cell, in that case what I have to do is, we have to drive both BI and BI hat lines, BI complement lines, halfway between 0 and 1 logic. So if the 0 logic is voltage 0 and 1 logic is the voltage 5 volts, then for reading purpose, I have to drive both the lines to something like say 2 volts or 2.5 volts. Okay. So driving these two lines, BI and BI complement, to a voltage in between 0 and 1 logic level, and then selecting this cell through this word line Wj, okay, you will find that then whatever is stored in this particular cell, these lines BI and BI complement will be driven accordingly. Okay. So that is sensed by this sense amplifier, and the corresponding output comes to this output line Di. Okay. So if we implement the cell like this, in that case you find that the number of logic, number of transistors that is required is much less compared to the number of transistors that is required in this type of implementation. Okay. So this is the basic architecture of static RAM cells and static memory organization. But as we said, that these static RAMs are mainly used for implementation of cache memory, whereas whenever we go for implementation of dynamic implementation of the main memory, we don't use static RAMs, rather we use dynamic RAMs. So let us see what is the organization of a dynamic RAM. In case of dynamic RAM, the RAM cells are very simple. It is simply like this. So this is word line Wj, and this is for a particular column, say Ci. Okay. The other part, that is the write sense amplifier and driver, which is almost similar to that in case of static RAM cell. So this is sense, write, amplifier, and driver. Okay. And as before, I will have a number of buffers. This is connected to output data line, say DI. Okay. I have the other control circuitry. And here I have column select. So dual rail in case of static memory cell is replaced by a single rail, which is PI in this particular case. And this is the basic cell architecture of dynamic RAM. So this is a dynamic RAM cell. Okay. So in this particular case, a bit 1 is stored in this cell whenever this capacitor is charged to a high voltage. If the capacitor is discharged, that means that bit that is stored in this cell is 0. I don't have any latch. So if I want to store a particular bit, say 1, what I have to do is this BI line, this single rail BI has to be driven to a high voltage, and after that you have to select this particular cell through this WJ line. Okay. And since BI is driven to a high voltage and this cell is selected, that means the path from this BI line to this transistor is on, to this capacitor is on. This is a capacitor, in which case the capacitor will be charged and it will store a value 1. Okay. If I want to store a value 0, what I'll do is I'll set this BI line to low. After that, I'll select this cell through this WJ line. So if the capacitor was charged previously, this will now be discharged. So it will store a value 0. Now if you compare the circuit complexity of the dynamic RAM cell with the static RAM cell, this is static RAM cell. So obviously you find that the number of components in the dynamic RAM cell, in the DRAM cell, is much less than that in case of SRAM cell. So that is why the packaging density of the DRAMs is much higher than that in case of SRAMs. Okay. And that leads to cost reduction in case of DRAM. But simultaneously I have other problem. In case of SRAM, even if you read a value from a RAM cell, the value contained in the RAM cell is not changed because the value is already latched. In case of dynamic RAM cell, you assume that the value stored in this cell was 1. That means the capacitor was charged. Whenever I want to read this cell, what I have to do is I have to select this cell to this line Wj. Then the cell will be selected. The value stored in the capacitor, the charge stored in the capacitor will be sensed by this BI. TBI line. The moment you try to sense it, this capacitor will get discharged. That means whenever I want to read a value, the capacitor will be discharged. So this is what is called a destructive readout. Right? So I have to have an arrangement that, because I know that whenever I read a RAM cell, if it was storing a value, if it is storing a value 0, then there is no problem. But the problem comes if it is storing a value 1. So whenever I want to read a RAM cell and the RAM cell was containing a value 1, the capacitor is going to be discharged and the value is going to be lost. Okay. So I have to have an additional facility that whenever you read any RAM cell, I should be able to refresh the RAM cell back. That means whatever value is read, the immediate next action should be you write the same value in the same RAM cell, which is called DRAM refreshing. That means after every read operation, the DRAM has to be refreshed. After every read operation, the DRAM has to be refreshed. Not only that, if I leave this RAM cell just like this, without any reading operation, even then the capacitor will be discharged because of leakage. So even if I don't read the DRAM location, I should refresh the DRAM at regular intervals of time. That means I have to have a mechanism by which the DRAMs can be refreshed at regular interval of time, or it will be refreshed after every read operation. Okay. So details of all this DRAM architecture we'll see in the next day.